Hello.
Hi, Emma.
Hey, how are you? Nice to
Hi,
see
how
you.
are you? Oh, let me adjust my. Okay, this camera is good. Okay. Oh, by the way, Emma, this is a Zoom's webinar, so people can hear us and talk to each other. Yeah.
Perfect. Yeah,
Okay,
yeah.
good,
No,
good. Yeah.
fine.
Yeah. How are you?
I'm good. What's the building behind you? It's super cool. What the your
Oh,
Zoom app?
this is a virtual background. It's actually the University Town Center, which is student accommodation and NUS. So it's nice.
Wait, those are the dorm. That's where students like live, or
Yeah, I think the taller building are the dorms.
I
The
got you.
flanker building is a canteen plus Starbucks plus gym, I think.
Nice. Wow, super nice. Yeah, I've never been to NUS. I've always been curious to visit. So no.
Are you coming for iClear in Singapore?
I am not. No, but yeah, no. It seems like a great location for a conference.
Yeah, it's
Um,
that place.
uh, Where does I mean iClear is huge. Also, does it, where are they going to host it? Do they have a? I assume you have a venue which is big enough to.
It's not in US. It's in a place called Expo, which is like an exhibition center in Singapore.
I see.
People show like aircraft or auto show all there. It's a big place.
Okay,
Only thing is
cool.
far away from downtown. It's like probably 30 minutes drive. Yeah.
I see. I see. Nice. Okay. Do you want me to share my slides or what should I do?
Yeah, you can share a slide. Let's try that.
All right. Let me do that. Give me one sec. But let me go to the beginning. Okay. I'll just share my entire screen, and then which one should I share? Maybe I'll share the little one, share. And then, okay, so how's that?
That's great.
Okay, cool.
Yeah.
So,
Oh, yes, go ahead, please.
oh, I was just gonna ask who typically attends, what's the background of the audience participants?
Very good. I can see most of the audience, they are actually students in NTU, NUS and NTU, which are the two universities in Singapore, but there are also other people from either just like the public of like in Singapore or from other part of Asia. I can according to the name, I can recognize a few names. Other people I don't know. So yeah, but most of them are students.
Cool. Yeah. No, thanks so much for inviting me to do this.
Yeah. Do you mind if I record the video? Of course, I will send will share with you to prove before we put on YouTube.
Sure, totally fine.
Yeah, thank you. Um, Maybe we can wait for like 2 or 3 more minutes. I can see people are still joining.
How do you prefer to do questions?
So, okay, for Emma and the audience, so the question, the Q&A tab in the lower functional bar is enabled. So you can either put your question in the question tab, or you can ask Emma. So Emma, do you want to all the question be like asked at the end of the presentation, or do you like people to raise hand during the talk?
Either way, it's fine to ask questions throughout the talk. The only problem is I can't necessarily see if they're raising their hand, so feel free to just interrupt me if
Sure,
you have.
sure. So if you have a question, you can also raise your hand, and there's a function in Zoom and raise your hand. Then if I see that, I will interrupt Emma at the appropriate time, and I'll let you ask a question. Then I'll enable you to talk. I think, or you can put it in the Q&A tab. Great.
And we have an hour for when, how much time do we have?
I mean, how much time you need?
I don't know. My guess is this is about a 40 or 45-minute talk, but honestly, I can spend however long well, within reason. At some point, I have to
Yeah,
get out of
it's
here.
all right. Yeah, okay. Yeah, I think 45 minutes talk and a few minutes for Q&A will be great.
Wait, is it Friday there?
It's Friday here. It's actually a holiday here in Singapore.
Oh, wow. What's the holiday?
I mean, so in our university, it's called a Well-being Day. So, and on Monday, it is a holiday of the Malay culture in Singapore. So it will be 4 day long weekend. And you,
Oh, lucky you. That's
yeah,
great.
yeah,
Okay.
nice. Yeah,
Yeah. Well, thanks for showing up on a long weekend. That's kind
yeah. Great. Maybe I can give an introduction to Emma. So thank you so much for coming to this talk. So AIT Talk Singapore is a AIT Talk series, primarily organized by students and the NUS, NTU, and beyond. And I'm helping coordinating and inviting speakers. So today it's a great honor to have Emma Pearson from UC Berkeley. She is an assistant professor from computer science at UC Berkeley, core faculty in the computational precision health program. She developed data science, machine learning method to study inequity and healthcare. Her work has been recognized by Best Paper, Poster, and Talks Award, and NSF Career Reward, Rhodes Scholar, Hertz Fellowship, Rising Star in ECS MIT, and the MIT Technology Review 35 under 35, Forbes 30 under 30, and the AI 2050 Early Career Fellowship, and the Samsung AI Researcher of the Year. Her research has been published in many great venues such as Nature, JAMA, New England Journal of Medicine, Proceedings of National Academy of Sciences, and Nature Medicine, ICML, iClear, and so on. She has also written for New York Times, 538, Wired, and various other publications. Now let's pass the time to Emma. Thank you.
Thank you so much for inviting me to give a talk. It's a real pleasure to be here, and thank you for showing up on what I understand is a holiday. I appreciate that as well. Wonderful. So today I'm going to be talking about using machine learning to increase equity in healthcare and in public health. I want to open this talk with a story. A couple weeks ago, I had the chance to meet with a doctor who had actually treated me when I was a baby. This woman is now 87 years old, and she is still doing research. She's been doing research for 50 years, which was pretty amazing to me. She's still running a research lab, so I hope I'm still doing as well when I'm 87 years old. And she said to me something that I thought was really striking. She said, "I'm still as excited as I was day one, but I have a lot more tools and toys to work with." And, I'm a lot younger than she is, but that very much describes how I feel as well. I've been interested for a long time by sort of old questions around health and social equality. How do we make the world a healthier and more equal place? But I feel like I have a lot of new tools and toys to work with. Recent years have brought me an explosion of new tools, both data and machine learning methods, to try to answer these old questions. And so to give some examples of this, we've done past work on mobile health data, which is the type of data that only became recently available. In work we published in Nature Human Behavior, we provided the first decomposition of women's mood, behavior, and vital signs into 4 simultaneous cycles: menstrual, daily, weekly, and seasonal, which had never been possible to do before. We've worked with mobility data, which measures inequality in human movement patterns. We use this to develop a model of how COVID spreads across fine-grained human mobility networks, linking neighborhoods to points of interest, improving our understanding of how inequality in mobility gives rise to inequality in infections. This work informed policy both nationally and internationally. We've also used mobility data to more accurately measure what we call socioeconomic segregation, which is basically how much the rich and the poor actually mix. And intuitively, if you know where everyone goes from their cell phones, you can get more accurate measures of this sort of thing. The commonality that all these projects have is that they rely on data sets that are new and rich and granular, and they enable us to come up with new insights in response to old questions. So this data is full of gold. But the gold is hard to mine because these data sets are huge and they're rife with imperfections and biases and noise. And so without sophisticated statistical and machine learning methods to compensate for those issues, you can end up getting wrong answers or getting biased answers. So today I'm going to tell you 3 stories under this theme from our very recent work. The first is around using dashcam data, image data, to try to quantify inequality in policing. The second story is about using text data to try to predict target variables and characterize disparities. And the final story is about using address data to try to map out fine-grained migration patterns. And I'll just say this is very, very recent work. I think 3 of the 4 papers I'll be talking about today are from 2025. One of them literally came out on arXiv I don't know, 90 minutes ago or something like that. So it's a pleasure to share it with you today. Okay, so let's start by talking about dashcam data. Okay, so this is a joint work led by Matt Franke and with JD's Fresco Pereira and also with Wendy Chu. Okay, and so what we're going to try and measure in this paper is police deployments. So what do I mean by police deployments? This is basically how much, how heavily are police deployed in different areas of a city. So sort of how many police are there in a given place, on the sidewalks or driving around, and so on. Why do we care about police deployments? Well, certainly in the United States, but also internationally, we're quite concerned about inequality in policing. Might some groups be more heavily policed than others? This has been, the target of sort of protests in the United States and also internationally, of course. And so, we worry about inequality in policing, and a lot of inequality in policing flows from where are the police in the first place, right? Intuitively, the police can't search you or arrest you or use force against you unless they're there in the first place. So where the police are deployed in the first place really, really matters. But in the United States and also internationally, it's been very hard to get data on where the police are deployed. And they don't even want to release this in aggregated form. And so, I totally understand why the police might not want to tell you where every single officer is at all times. Intuitively, it would make it much harder to do their jobs if that were true. What I don't understand, though, is why citizens shouldn't have a right to know even how many police are sent to a given city or in a given area of a city, because that's the kind of thing that people should be allowed to be aware of and weigh in on in case they want more police or fewer police in their area. And even that data has been basically impossible to get. Okay, so what did we decide to do? We decided to find the police. And how are we going to do this? Well, we took 25 million images of public street scenes throughout New York City. So on this slide, I'm showing you an example of one such image. Where do those pictures come from? Well, basically, they come from Lyft and Uber drivers, so sort of rideshare drivers, driving around the streets of New York City. Some of these drivers have cameras on the front of their cars. They have this for like insurance purposes, for example, in case they get into an accident. And so we have all those images. And so what you should think of is it's very fine-grained street scenes throughout New York City, sort of pictures of the city. There's a lot of other things you can do with this data, by the way. Okay. So what are we going to do? We're going to take these images and we're going to train a model to detect the police cars from the dash cam images, and we're going to use that to sort of map out inequality in policing across the city. And in particular, what we're going to try and estimate is the probability that residents of a given group, so for example, Asian residents of New York City or Black residents of New York City or rich residents of New York City, have a police vehicle visible when they are on a street in their home neighborhood. Now, this data set has various biases, and this method has various biases that you have to compensate for. Here are two. The first is that the locations are non-representative. So, basically, we have more images in some parts of New York than others. And so the way we deal with this bias is we basically reweight the image distribution so it matches the population distribution. So if we were trying to estimate police deployment levels for Asian residents, we would upweight areas of the city that had a lot of Asian residents. And if this is basically an inverse propensity weighted classifier for those interested in the methodological details here. A second bias you might worry about is sort of imperfection in the computer vision classifier. So like, the classifier that detects police cars is not going to be perfect. It's an AI model. It's going to have some false positive rate, false negative rate. And intuitively, you could end up with biases in your estimate if you fail to account for that, first of all, or secondly, if that false positive rate and false negative rate varied across groups. So if for some reason the model could never detect police cars in Asian neighborhoods, then that would lead to an underestimate of police presence in those neighborhoods. So the way we deal with this is we actually explicitly estimate and compensate for imperfect false positive and false negative rate. We also test for disparities in performance across subpopulations to avoid that sort of bias that I was just telling you about. Okay, there's some other biases we can't compensate for. I'll come back to those at the end of this part of the talk. Okay, so what do we see? First of all, the model for detecting police cars works pretty well. So here I'm just showing you a couple examples of images where we detect police cars. Those are sort of in those purple boxes. And you can see it's doing a good job of picking them out. For those of you who actually want to see systematic statistics, like both the AUC and average precision of this classifier are very, very high. Why is this? Probably two reasons. One is that Matt, the first author on this paper, did a really excellent job training the classifier. Like, he got a ton of labeled data, he did a lot of iteration, so on and so forth. The other is that police cars are pretty straightforward to detect from the image data. And this is one strength of this method, is that you can actually do a good job at the detection task because the cars are like big, they're consistently labeled, stuff like this. Okay, so now we've got our classifier. It works pretty well. We feed it through our statistical pipeline to kind of remove some of these biases, and then we map out disparities in policing across the city. So what I'm showing you here is a map of New York City, and red indicates areas with higher police deployment levels, blue indicates lower police deployment levels. And the main point from this map is that there's a lot of spatial variation. There's like a factor of 20 variation across the different neighborhoods of New York in how many police cars there are. And if you want to break that down by the different sort of sub areas of New York City, so New York City has 5 major sub areas, and in Manhattan, which is sort of the most famous area of New York City, there are much higher policing levels. That on its own is probably not all that worrisome. Like Manhattan, it's been the target of terrorist attacks in the past. It's like got a lot of expensive commercial real estate. Like it's probably not that surprising. There's a lot of police cars there. More concerning, though, is that you also see evidence of racial disparities in policing levels, which is concern because there's a lot of concern about racial inequality in policing in the United States. So, sorry, there's a house alarm going off near me, but that's hopefully okay. It should stop in a couple minutes. Okay, so we basically see that there are higher policing levels for Black and Hispanic residents of New York then there are sorry, give me 1 second. I actually should deal with this. Give me 1 sec. Okay, good.
And Eva, I think there is one question from audience.
Oh, perfect. Okay.
I'll allow Yongyi to Andrew to talk. Yeah, Andrew, go ahead.
Can you hear me?
Yes, I can hear you great.
I want to know, does Asian mean East Asian or South Asian or both?
Yes, that's an excellent question. We're following U.S. Census categories here, which groups together East Asian and South Asian residents, which is an imperfection in U.S. Census categories that we could go into. But yeah, that's the coding here.
Okay, thanks a lot.
Yeah, good question. Okay, fine. So we see evidence of sort of racial disparities in police deployments where you see sort of higher levels in Black and Hispanic neighborhoods than in white and Asian neighborhoods, which is potentially of concern because there's been a lot of concern about sort of racial biases in policing against Black and Hispanic residents. Now, I want to be very clear. We are not claiming that this is proof of racial bias. Rather, we are claiming that this is something potentially concerning that residents of New York have a right to know about. We also see evidence of sort of socioeconomic disparities in police levels, where sort of in lower income neighborhoods, you see higher police levels than in higher income neighborhoods. And this too is potentially of concern. Okay. Now, I mentioned there are some biases we can't compensate for. One is that like police vehicles are only a partial proxy for all policing activity. So like, for example, we can only detect marked police cars, but you've also got police driving around in cars that are not marked. We can't detect those. Those just look like ordinary cars. We can't detect police on foot. We can't detect police in the subways, underground. So there's various imperfections there. Secondly, we reweight at sort of the census area level to match a non-representative population distribution, but we can't reweight at the sub-census area level. So sort of if there's biases within each census area, that's going to introduce biases in our estimates. Okay. So to conclude, a couple things here. First, we think it's very important that the police themselves release better policing data. We find some evidence of disparities. I think those disparities are potentially concerning, but this is not a realistic way for ordinary citizens to exert oversight. Like, we had to get this proprietary data. We spent tens of thousands of dollars on GPUs. We annotated tons of images. Like, come on, regular citizens can't do this. It would be easier and more accurate for the police just to release this data themselves so that, citizens can keep an eye on the police who are, whose salaries they're paying and so on and so forth. Okay. This work has had sort of some impact locally within New York. It's gotten press coverage. It's also gotten attention from public defenders who are, sort of the people defending people who are accused of crimes. They're worried about disparities in policing. And if you're interested in the paper or the data set, you can find them both online. By the way, the data set might be of interest to you. We've released a lot of the images. So if you're just interested in sort of doing AI on computer vision models or, studying sort of city scenes, this is a good data set for that. And I'll say in follow-up work, I mentioned there's a bunch of other stuff you can detect from this. I happen to be interested in policing. I've done a lot of work on policing, but there's a lot of other stuff you can detect. One thing we've done is detect floods within New York City. So flooding has been a big problem in New York City. It's been an increasingly bad problem, probably due in part to climate change. And you can sort of see, I'm showing you some images at the left of sort of during a particularly bad flood. You've just got like water on the streets. It's like not safe to drive, like water pouring into people's apartments, bad stuff. And this is happening in many other cities as well, of course. And so what we did basically was we used vision language models. In this case, we didn't even create a trained data set at all. We just used vision language models and did classification zero shot. We basically asked, can you see a lot of water in this image? It turns out this works pretty well. We then apply a Bayesian model to sort of clean up some of those classifications. If you're interested in the details of that work, it's also online. Okay, any questions on that before I go on to the second part of the talk? Okay, let me move on to the second part of the talk. Okay, so this is about using text data. Of course, people have been very excited about text data, large language models, so on and so forth. We're excited about them too. And I want to tell you about some of our recent work there. In particular, this is joint work with a ton of great co-authors. It's based on a paper which is just recently on arXiv and also a paper published recently in the New England Journal of Medicine AI. Okay, so, I'm quite interested in how we can use text data and use large language models to study the things I care about. And one of the things I really care about is bias and inequality. And people are very interested in how LLMs relate to bias and inequality. But most of that work has really focused on how could LLMs be biased? How might they have racial biases or nationality biases or language biases or a million other things, right? How might they be biased? And this is really important and valuable work. But I'm also quite interested in how we can use them to improve social equality in various ways. If you look at papers which focus on sort of equity impacts, about 85% of these papers focus on harms, and only about 15% of them focus on opportunities. I know this because we actually spent a while counting them. I think LLMs have created really important new equity-related opportunities. So that's what we talk about in this paper, and this is joint work with Raj Mova and with Divya Shanmugam and with John Kleinberg, among many other excellent co-authors. And in particular, in this paper, we talk about 3 possible applications of LLMs to improve equity. The first is using large language models to detect bias from text, for example, in clinical notes or in medical textbooks. We know that people can have biases and that those biases contribute to social inequality. So, for example, in health systems in the United States, doctors describe Black patients as difficult more often than they describe white patients, and this can potentially lead to a lower quality of care. And previous research has shown that LLMs can improve our ability to detect this human bias from text data by allowing us to do more than just do simple keyword searches for the word difficult to more precisely characterize subtle linguistic biases in sentiment or in tone or in stereotypes. A second application we're quite excited about is using LLMs to create structured data sets from unstructured text. So structured data sets here, I just mean are data sets that track a standardized set of fields in a consistent way, and they allow us to measure inequality and develop policies to mitigate them. But creating these data sets often requires a lot of substantial human effort to extract the necessary information from raw text data. So to give an example of this, activists all over the world scour news articles to try to create databases tracking violence that disproportionately hits women, so sort of gender-based violence. And it's really time intensive to create these data sets because they have to read all the news articles and extract the structured information by hand. It's also kind of traumatizing to do because these articles are upsetting. And so LLMs can accelerate that kind of work by making it much faster and easier to extract structured data from unstructured data sets. And then finally, we're quite interested in applications of these models to improve equity of access to information. So in a healthcare setting, they could help provide answers to patient questions for patients who lack easy access to a medical provider. Okay, so in the paper, we sort of lay out some of these use cases that we're excited about and want to encourage other researchers to pursue. But now I want to talk about a follow-up paper we wrote trying to perform a specific task and provide a method for doing this specific task. And specifically what we were trying to do here was use LLMs to identify interpretable text features which predict a target variable. And I'll explain more what I mean by that in a second. This is applicable to detecting biases in text, but it's also much more broadly applicable. And this is joint work led by Raj Mova and by Kenny Payne. So let me give you some examples of this task to sort of make this task more concrete. Here's how you might use it to study bias. You might say, what text features in a police stop transcript predict whether the officer is speaking to a white driver or a Black driver? And if some of those features seem suspicious, then maybe it's indicative of bias. Or what text features in a doctor's clinical note predict whether the note belongs to a male versus female patient or a Black versus white patient, or so on and so forth. And these aren't hypothetical examples. People have actually written papers on exactly these tasks. Even if you're not interested in bias, this is also a task which is very useful more broadly. So for example, you might care about what features of a social media post predict whether it will go viral, or what features of a restaurant review predict whether it will get a high rating, or what features of a clinical note predict whether a patient will develop cancer. And because this is such a sort of broad task with a lot of applications in the health and social sciences, it actually has a name. People have been referring to it as hypothesis generation from text. And there's been a lot of prior work on it. Prior to the rise of LLMs, people were already working on this task, often using sort of classical NLP methods like fighting words or topic modeling and so on and so forth. And so these are sort of classical statistical methods that do not rely on large language models. It's plausible, though, right, that you could do a better job of this using large language models simply because of their sophisticated representations of text. And indeed, multiple lines of work have sought to do exactly that in recent years. So how might you do this if you wanted to use LLMs? How might you identify interpretable text features that predict some target variable? Well, one reasonable thing you might do is give an LLM, let's say you were trying to predict, let me give you like whether a headline will get a lot of clicks. Well, you might give an LLM, headlines that got a lot of clicks, headlines that didn't get a lot of clicks, and ask it to hypothesize what features are different, right? And that's like a totally reasonable way to do this. And in fact, there's a paper written doing exactly this. The problem with this, though, is it's not all that scalable, right? Like if you've got a data set with 1 million pieces of text, you can't give the LLM a 1 million pieces of text. You can only give it a couple of examples at a time, both due to context window limitations, but also because models are just not that good at sort of reasoning systematically over vast text data sets. Another totally reasonable thing people have tried is, they might take some model and fine tune it to predict the target variable, and then try and interpret its neurons and hope that the neurons are interpretable. The problem with this is that neurons don't tend to be interpretable, right? One neuron can often encode many different concepts at the same time, and so it's just hard to interpret neurons. So the basic challenge in a nutshell is that if you want to efficiently and scalably learn statistical relationships, you need numerical representations of text, like neurons, embeddings, right? But interpreting these neurons is often very hard. So we propose a new approach called hypotheses. This name was controversial. We argued about it for a lot. So if you don't like it, please don't tell me because there was much debate. And I'm going to explain to you how this works. And the running empirical example I'm going to use is what features of a headline predict engagement, predict how many people are going to click on it. Our approach is motivated by a theoretical result, which we derive, which we refer to as a triangle inequality for hypothesis generation. And the result in a nutshell is, if a neuron is predictive of a target variable, then a sufficiently high fidelity interpretation of the neuron will also be predictive. So this theoretical result motivates our 3-step procedure. In the first step, feature generation, we learn interpretable neurons. Then in the next step, feature selection, we select the neurons that predict the target variable. And then finally, having selected that subset of interpretable and predictive neurons, all we have to do is interpret them by generating high-fidelity natural language explanations of the neurons. So that's the procedure in a nutshell. Now let me unpack each of these steps for you. So the first step, generating interpretable features. How do we do this? Well, we train a sparse autoencoder on text embeddings, and then we use the neurons of the sparse hidden layer in the autoencoder as our interpretable features. Sparse autoencoders, to be clear, are not our innovation. The innovation is applying them to this task. So how does a sparse autoencoder work? Well, basically what you do is you start with a text input, and in particular, an embedding of that text input. So we're just going to take like OpenAI embeddings of our texts. And here I'm just showing you for a particular headline, I was surprised at the largest buyer of elections in my state. And then we're going to take the OpenAI embedding of that. And you could do this with any other embeddings as well, of course. And so then what you do is you feed it through a neural net, and in particular, the sparse hidden layer of the neural net, all the activations in that hidden layer, except for the top K activations, are going to be set to 0. And it turns out that that sparsity will encourage interpretability of the neurons in that hidden layer. And then finally, the neural net is going to attempt to reconstruct the original input from the sparse hidden layer. So from just those K activated neurons, it's going to attempt to reconstruct the original input. So in particular, the loss is going to be the reconstruction loss. How accurately can it reconstruct the original embedding? It's a little more complicated than that. You also train an auxiliary loss to avoid the bit latence. Happy to go into those details if it's of interest. But the basic idea is it's an autoencoder, right? So it's going to try to reconstruct the original embedding, but it's a sparse autoencoder in that the hidden layer is constrained to be sparse. So empirically, past work has sort of found that sparse autoencoders seem to learn interpretable features. Why might this be intuitive? Let me give you some hand-wavy intuition. The idea is that the architecture is leveraging the fact that natural language is sparse. Any particular text is only going to express a small fraction of concepts. And so if you sort of constrain the architecture to be sparse, you might end up learning sort of human interpretable concepts. Okay. So now we've, learned our hopefully interpretable features. Next step, feature selection, very simple. We're just going to use lasso to select the most predictive features. And then finally, okay, so now we've, taken our neurons, we've gotten hopefully interpretable neurons, and we've filtered for the set of them that actually predict our target variable. Now we've got to interpret them. This is also known as auto-interpretability. It's sort of a whole field unto itself. And how are we going to do this? Well, we're going to sample texts that highly activate each neuron and texts that do not. And then we're going to give it to an LLM to explain what differentiates them. So in the case of, one particular neuron, the neuron I was showing you, examples that highly activate the neuron might be like, they went to rescue a hurt little dog hiding in a bush. What they found was a big surprise. Or over 20 years ago, a little girl stunned people from around the world with 5 minutes of wow. Okay. So if you had to identify the common thread here, it might be like, does the text mention someone is surprised, right? And indeed, when you give this to the LLM, that is the hypothesis that it comes up with. Okay. Any basic questions about the procedure here before I explain to you the results? By the way, if you're like, does this actually work? I'm about to provide some evidence that it does. But if you're confused about what we're even doing, I'm happy to explain. All right. So it's not obvious this procedure should actually be useful. Let me just give you an example, by the way, of what it does on the headline example. So again, here the task is predict whether a headline is going to get a lot of engagement, it's going to get a lot of clicks. And so I'm showing you like green features are things that are associated with more clicks, red things are associated with fewer clicks. And so, for example, mentioning actions or initiatives that positively impact a community is associated with fewer clicks. Mentioning the environment is associated with fewer clicks. Addressing collective human responsibility is associated with fewer clicks. So like, I find this slightly depressing. Like, it's not great if like people don't want to read about the environment. The environment is pretty important, but whatever. That is apparently how the online news works. Okay, so let's do more systematic experiments. We're going to compare to 3 different LLM baselines. Happy to provide more details about these if they're of interest. One thing I should mention is that 2 of these baselines are actually pretty expensive to run, especially relative to our method because they have to do a ton of LLM queries. So our method is actually several orders of magnitude cheaper and more scalable. That's a big advantage, but we still wanted to compare to these methods fairly. And so we basically the way we did this was by spending a lot more money on them than we did on our method. Okay. So the first thing we do is we say, okay, let's generate synthetic data sets where we know the hypotheses, and then let's test if the methods can recover them. So for example, we might have a Wikipedia data set and the synthetic hypothesis is the Wikipedia article is about a Simpsons episode. And we assess how well the methods can recover this hypothesis using 3 different methods. One is just the F1 score between the true and recovered hypothesis. The second is how similar does GPT-4 assess the 2 hypotheses to be. And the third is AUC for predicting the outcome. And what we find is, we've got 3 data sets and we've got 3 metrics. So that's 9 sort of comparisons. And we find that hypotheses wins on 8 out of 9 of these. On the remaining one, it like loses slightly to one baseline. So in general, it outperforms the baselines on synthetic data. But like, okay, synthetic data, is it really all that realistic? So then we also take 3 real data sets. In particular, we look at features of news headlines that predict engagement. So that example I was just showing you. What features of reviews predict rating. And finally, what features of US congressional speeches predict whether you'll be a Democrat or a Republican. So what party you're in. And the metrics we use are, first of all, what's your predicted performance? So how well do the hypotheses explain the outcome? And secondly, how many unique distinct hypotheses do you actually get? We might care about this as a scientist because we want to have more directions to pursue. We don't want just like one hypothesis, we want like a bunch. So, okay, what do we find? Well, we find that hypotheses does tend to have better predictive performance. It also has many, many more generated hypotheses. When you do sort of a regression of how many of these remain significant on a held out data set, we find that 45 of them remain significant compared to 24 for the next best baseline. So to give an example, here I'm showing you the results on the headline data set again. The results for our method are at top. You can see it's just generating a lot more hypotheses than the baselines, and which are just not generating as many ideas. And then a final test we do is like, well, the real test is like, okay, on a data set that people have studied well, can you find new stuff? And so what we do is we take data sets that have been thoroughly examined by prior work, and we see whether our method can discover new things. So for example, there's like a very famous study of speeches in the US Congress, just trying to sort of say like what bigrams and trigrams predict whether you're a Democrat or a Republican. And, it's a very well-studied data set. And what we find is that when you use our method and compare it to previous methods, you get a much better AUC. And furthermore, most of the hypotheses we discover remain significant, indicating that we can actually add signal over and above previous methods and discover new things. We also find sort of qualitative benefits relative to methods that people have been using previously. So like the problem with bigram methods, which is just basically looking at like what two-word phrases appear more commonly in one data set than another, is that you get stuff like oil companies. And like, if you're not familiar with like a lot of context about congressional speeches in the United States, it's like kind of hard to know what is the context here. In contrast with our method, you get stuff like criticizes oil companies or oil industry practices, which is like much more specific, right? And it tells you that one party doesn't like oil companies and is criticizing their practices, as opposed to just like, I don't know what's going on here. There's also just some stuff which is really hard to capture in 2 words that our method can capture, like criticizes government resource allocation, hiding disparities between domestic needs and actions abroad. Like that's a pretty complicated idea politically, and like I challenge you to express that in 2 words. Like that's pretty hard to do, right? Okay, we do another study of another data set. I actually just wrote to the author of this paper, and he basically we find similarly that that you can sort of improve AUC and find additional hypotheses. Okay, so to summarize, we present hypotheses. It's a general method for hypothesis generation in text data sets. Specifically, it identifies text features which interpretably predict a target variable. We outperform strong LLM baselines on both synthetic and real data. It's a lot cheaper. It's more scalable. It discovers new stuff, even in well-studied data sets. We are releasing, that should be past tense. We have released a software package to facilitate use. You can, install it in 2 lines of code. I've like run it myself. It's very easy to use, in my opinion. You can find all this stuff online. And we're actively looking for exciting places to apply this. We'd love this to sort of be used both within computer science and within social sciences, health sciences. So if you've got exciting ideas, feel free to reach out. Any questions about this before I go on to the final part of the talk?
So I have a question. So just the overall how this hypo sparse autoencoder work. So basically you train a sparse autoencoder and you use it to extract potential different topic from a piece of text. And so that list of topic will serve as a feature for certain downstream task. Am I right?
Yes, correct.
Okay.
Yeah, that's it. Yeah, that's exactly. So the training of the sparse autoencoder doesn't use any information about the target we're going to seek to predict. The purpose of it is just to identify interpretable features in the first place.
Great.
Right? And then we're going to filter those and interpret those. Yeah. This wasn't the question asked, but I will mention, I think an interesting thing to do would be to jointly train the SAE, where you don't just train it on the reconstruction loss, you also train it to try to predict the target variable in that inner feature, in that inner layer, right? You could have a joint loss, and like we didn't do that. I think you could try that. I think it'd be interesting.
Great, thank you.
Cool. All right, final part of the talk. Okay, using address data to infer fine-grained migration patterns. And this is a paper that just came out an hour ago, and it's joint work with a bunch of excellent co-authors, and in particular, it's led by Gabriel Agostini, who is a PhD student at Cornell. Okay, so migration, which is just like how many people move from one geographic area to another, really, really matters. It matters nationally, it matters internationally. It captures stuff like responses to environmental disasters and climate change migration. It captures people moving to areas with more jobs or economic opportunities. It captures social change, right? People moving from one area to another. It captures how people are responding to the COVID pandemic. Like just like where people move over time, it influences like a whole bunch of downstream stuff, and we really care about. But within the United States, migration data has been very, very bad. Basically, you've got like publicly available data that basically captures migration flows on a county to county level. So a county within the United States captures, and it can capture up to like 10 million people. I'm pretty sure the largest county in the United States is 10 million people. That's just like a huge area. And in particular, many phenomena we care about are like much more fine-grained than that, right? So if people are migrating in response to a flood or a wildfire, it's not like the whole county is going to leave. It's like people, are going to leave on a much more fine-grained spatial scale. And within the United States, about half of moves occur within county, and you can't see that at all in this data. These people appear to just stay put, right? Okay. An alternative to this is sort of proprietary data. So you can buy data sets, which basically will give you a list of a person and their addresses. So here's an example for me. These are not my real home addresses. These are my work addresses. But anyway, here each row in this data set is just like a name and an address and a date. So it sort of gives you some measure of how people are moving over time. And these data sets have been widely used because they're really, really granular. Like they tell you where individual people are moving, but they've got significant drawbacks. One big drawback is they're not publicly available. You got to pay like a lot of money to get access to these things. Even if you do get access to them, they require a lot of time and resources to process. These are sort of many, many, hundreds of millions of rows, and it's just difficult for people to process. But I think the most fundamental difference, the most fundamental difficulty is just like, this is proprietary data and it's like not all that well documented. And it's just very unclear, like, what are the noise, like, what's the biases, stuff like this. It's just like, is this actually a perfect picture of everyone in the United States? It's definitely not. And I should give a little more context on this. This data does not come like there are people within the United States who have a pretty good view of where everyone goes. Like the U.S. government would have a pretty good view of this because they, for example, you had to pay your taxes, and when you pay your taxes, you give them an address. So like, the tax agency within the U.S. would have quite a good picture of where everyone goes, but the tax agency is not going to make their data available to researchers, or at least not widely available to researchers. And so instead, you've got commercial providers who sort of, make a business out of compiling this data. They're not able to do nearly as accurate a job as the US government would be able to. And so their data sets are highly imperfect. Okay. So what do? We create a new data set, migrate. And this is a migration data set, which basically combines these two sources of data. It takes biased but fine-grained proprietary address data, and it combines it with more reliable but less granular census data. So it sort of takes the more reliable public data, which isn't very granular, and it combines it with the sort of proprietary data, which is very granular, but probably more biased. And what this results in is a data set which is very, very granular. So we get estimates of flows between 47.4 billion pairs of census block groups, CBGs, throughout the United States. And so a census block group, so while I said, the public data is basically counties, which is sort of, areas of up to 10 million people. In contrast, a census block group is an area of like at most a couple thousand people. So this is, many, many thousands of times more granular. And in particular, it's about 4,600 times more granular than 5-year county level data. It's about 18 million times more granular than existing state level data. So much more granular than existing public data sets. And we're also making this available for researchers. How do we do this at a high level? I could go much more into details if folks are curious, but the basic idea is we take the raw proprietary data, which comes from a data provider called Infutor, and we repeatedly rescale it to match census data sources. So basically, for example, we rescale each CBG, each sort of fine-grained geographic area, so it matches the known CBG population in that area. And similarly, we rescale to other sources of data. The statistical method we use to do this is based on what's called iterative proportional fitting in the machine learning and statistical literature. It's also known as raking in the demographic literature. The basic idea is you've got a matrix, you repeatedly rescale its rows and columns to match known constraints on those rows and columns. This has various nice statistical properties, and we apply related ideas here. That's the high level idea. There's also a ton of messy details here. Dealing with geographic data is hard. Gabriel did a superlative job of this, just like births, deaths, emigration, data contradictions, bad things, etc. Okay, so let me just show you some pretty pictures of what we found. So here on a national level, this is sort of plotting out migration rates, so sort of the fraction of folks who are leaving from each area. You can see it's pretty spatially fine-grained. It's actually kind of easier to see this if you zoom in a little bit. So here I'm showing you New York City, so just like, a tiny part of the country. And in the left, sort of smaller plot, I'm showing you what was available before. And in the right, I'm showing you what we've got now. So you can see, yes, definitely much more spatially fine-grained. You might say like, okay, like anyone can make pretty pictures. Is this actually like correlated with, external measures of ground truth? And we show that it is. So basically what we do is we look at the correlations between our data set, migrate, and external census data sets. We look at the correlations in populations, we look at the correlations in migration flows, and we find like quite consistently high correlations. There are various things you might worry about sort of pushing up these correlations in an artificial way. We sort of systematically look at stuff like that and find that it does not suffice to explain the high correlations. Happy to go into more details if folks are curious about what you might worry about here. We also compare our data set to the raw original proprietary data. So, the question is like, have our methods actually reduced bias or error in the raw proprietary data? And we find that it does. Specifically, we compare our data set, migrate, to external census data, which is sort of a ground truth. And we look at sort of how much error there is compared to the original proprietary data. And we find that it significantly reduces error. We also find that it significantly reduces bias. So if you look at the raw proprietary data and you just sort of plot the level of error in it, you find that it varies a lot. So here I'm showing you a map where it's sort of how much does the raw proprietary data overcount or undercount the county population. And you can see that, there's substantial overcounting and undercounting. There's also quite a lot of demographic bias, by which I mean like, the original proprietary data tends to like overcount people who live in rural counties and people who are older and people who are white and people who own their homes. And in contrast, our data set, migrate, you can see that has basically reduced those biases almost entirely to zero. Now you might say like, okay, well, what can you actually do with this data? One thing, you can do, as I mentioned, is you can use it to study migration in response to environmental disasters. In California, as you may know, there's been like a lot of recent and pretty terrifying wildfires. Really, if you've ever been in California during one of these things, it's like pretty apocalyptic. It's like the sky turns orange. It's frightening. It's awful. And so people have had to migrate in response to these things. And so, and we care about those migration patterns because like it helps us support folks who now need homes. It helps us know like, are they just going to come back to the same area and still be at risk? Like there's a bunch of policy reasons we care about this stuff. So what I'm showing you here are the two largest fires in California during the period where we have data, the Camp Fire and the Tubbs Fire. And what I'm plotting for you, sort of the shaded colors are sort of the outmigration rate. So the fraction of folks who are leaving those areas in our data. And you can see that our data is revealing very dramatic outmigration rates. Another really important point here is that, the fire perimeters, so those sort of red dotted lines, are much smaller than the county boundaries. So county level data is really not enough here because fires are affecting much smaller areas. So you need much more granular data to properly study them. And, if you want sort of a quantitative analysis, you can just sort of say, okay, in the migrate data, how does migration rate change pre and post the fire? So here I'm showing you dotted line is when the fire happens, and that red line is showing you how high is the outmigration rate for sort of census block groups, so sort of fine-grained areas within the fire perimeter. And you can see this big spike, right, in outmigration rates. And in contrast, CBG's census areas, which are not as affected, don't show that. So our data is sort of clearly revealing those spikes in outmigration. And it turns out that you really can't see this effect at all in traditional census data. It's just like not granular enough. So this is sort of an example of how you can use our data to very clearly study important granular patterns that you can't see from publicly available data sources. Okay, so to summarize, we're providing a new data set, Migrate, which is like literally online right now. It is thousands of times or millions of times, depending on how you count, more granular than public data. It's highly correlated with external ground truth data, and it's less biased than proprietary data. The paper's online, there's a website, there's data. Please make use of this. And if you do actually happen to make use of it, please let us know how it goes for you, because we're very open to feedback on this. Okay, so thanks again for your attention. I've told you 3 stories today. The first is around using image data to quantify inequality in policing. The second is around using text data to predict target variables and characterize disparities. And the third is using address data to infer fine-grained migration patterns. Thanks very much for the invitation to speak. And thanks in particular to my students who have led this work and have really just been wonderful people to work with. Happy to take any questions.
Yeah. Thank you so much, Emma. It's a great talk. Yeah. Any questions from the audience? If you're too shy, you can type your question in the Q&A tab, or you can raise your hand. So I got a question, Emma. Oh, okay. Actually, one question from the audience from Yang Yong. Emma, can you see the question?
I cannot, but I can stop my screen share perhaps, and then I can see Q&A. We're working on actually looking
on
for
the tab.
Yes, I see it. Looking for collaborators for a topic 30-day readmission predictive model with hospital electronic data, lab data, and climate change data. Yeah, I mean, feel free to shoot me an email. Always happy to chat about potential collaborations. I'd be curious to hear about what your data is and what you're looking to do. My email's just online. You should be able to find me.
Young is looking for collaboration.
What's SGH? Is that
a
Singapore
General Hospital?
I assumed. Okay, cool. Okay, yeah, shoot me an email.
Yeah, I actually have a.
What's the national NEHR database? Does Singapore have centralized health data?
I think Yang Yong, you can answer the question. I don't know what the NEHR data is.
National
database. Okay.
No, I'd be curious to hear more. Happy to chat.
Yeah. Okay, great. Yeah. Okay, so before there are quite a few questions popping up. Oh no, it's from Yang Yong. Okay. For example, when you are okay, I think the 3 data set you share with us is all about how do you process and utilize public available data. But for example, in Yang Yong's case, if it's something private and it's difficult to link them to other data set, which because they have to be siloed, how do you proceed with that?
Well, yeah, so I should be clear. Several of these data sets are not public data sets. So like for the migration project, we're working with proprietary data. Now we release a version of the matrices which are public because we want to enable, but the data set we're working with is very much not, and we are not allowed to release that because that's individual addresses with names. That's very sensitive data.
Oh, I see. Yeah.
But to answer your question, I mean, do you have specific questions about the nature of working with private data? I mean, in general, we try and be careful and so on and so forth, but yeah.
Oh, okay.
Yeah.
Good. Any other questions from the audience? Okay, if not, great, thank you. Great, thanks, Emma. And
no, of course. Yeah, no, thank you for the invitation. It was a pleasure. See you guys later. Have a nice weekend. Bye.